Thank you for being with us. We will respect your need to be away by very shortly after 3:30. Marek has done a lot of writing about cryptography, both in academic journals and also in the popular press. He's a great supporter of the work of the National Museum of Computing, and particularly the Turing-Welshman Bomb Rebuild Trust, which owns and demonstrates the bomb in the museum there. So it's a very special pleasure, therefore, to invite Marek this afternoon to talk to us about the inheritance, really, from the code-breaking activities that we've talked about here before. But Marek, over to you.
Thank you very much, Roger. Well, ladies and gentlemen, let me, for the reasons which are obvious for you right now, skip all those normally introductory talk. I'd just like to assure you that the presentation I'm going to deliver was very thoroughly checked with almost any antivirus program. So feel safe, at least from the site. I would try today to convince you that the wartime Allied code-breaking effort was one of the most important roots of the current digital civilization, if not the most important one. And let me start with the observation that nothing illustrates the changes which have taken place during the recent century better than the change of the meaning of the very simple word computer. In dictionaries from mid-20th century, if you're looking up the word computer, you would probably find something like a man or a woman dealing with any kind of computation. In fact, all those people you see in this instructional accounting video are computers, in a sense, attributed to the idea in the middle part of the 20th century. But the landscape of automated computing at the time was far more diversified than only accounting. In fact, some form of arithmometers, calculators, automated adders is a reality which probably most of us have experienced in our childhood. I remember my mother using an automated calculator to make some computations for her job. But that was not all. There was also a far more advanced form of automated computation, at least from the period of Newton. The scientists in the world used to describe the problems they were facing in terms of the differential equations. And differential equations tend to be very difficult to solve, at least for most humans. And therefore, people were trying to automate the process of solving the differential equations, constructing a device which is very inappropriately called differential analyzer. I'm saying that the name does not reflect the nature of the device. It's just due to the fact that what the differential analyzer does is integration and not differentiation. That's one of the best examples, most extensive examples. Those facts, of course, in America, sometime in 1940s, 1950s. But there was also one more threat, present mostly in the business, stemming from the invention by Hollerith, all the card processing, a very, very significant threat in automated processing. And I will try during my presentation to illustrate how all those three threads merged together over time into what we call today digital civilization. And I promised you to start from the code breaking. Yes, that's true, because code breaking, and in particular the advent of the ciphering machines, created a challenge which, in my humble opinion, resulted later on in the invention of the earliest electronic computers. Ciphering machine, the first one was probably patented by an American, Edward Hepburn, sometime in 1917. And another example, most famous ciphering machine of the world until now, German Enigma. They were game changers for a very simple reason. People used to hide their secrets behind the veil of cipher code for many centuries. People used to solve those puzzles also for many centuries. So the code makers were being assisted by the code breakers. There was some kind of equilibrium between both until the advent of the ciphering machine. Ciphering machine has put the accent decisively in favor of the code makers. That machine, Enigma, if you sum up all the construction elements of the machine and you transform them into a number of possible combinations, you reach the number of 3 to the power of 114. 3 to 1, 10 to 100 to 114. To illustrate the number for you, I can say that the number of the atoms in the observable universe is estimated at the level of 10 to the power of 80 only. So it's a number negligible in comparison with the number of possible combinations in Enigma. During the First World War, the British were recruiting code breakers from among the accountants and city brokers, thinking that those two professions are used to very high numbers. But unfortunately, the number of combinations generated by the ciphering machines was much higher, and it surpassed any ability of even the city stockbrokers. The advent of the ciphering machines created a complete shift of paradigm in the code breaking. So far, the code breaking was decisively linguistically oriented, because the codes, of course, they were hiding somehow the contents of the message, but they were unable to hide the structure of the language, of the clear text used as a message. And therefore, someone who was very familiar with the standard structures of the language was able to discern the context and to reveal it from its coded or enciphered form. And therefore, normal recruitment procedure for the code breakers during World War II and during World War I and after World War I was employing the linguists, the translators. To offer you as an example, you might have heard about famous telegram of Zimmerman telegram, which was decoded by the British code breakers, and their success caused the United States to join the Allies during World War I. Two people responsible for the break were one, a journalist from the German press, and the second one was famous for his perfect translation of the theological works. So they were linguists. And in fact, the leading British cryptographer of that period, Dilwyn Knox, was also a linguist. He was a specialist in Old Greek. Advent of the machinery, advent of the ciphering machine caused a complete shift in paradigm. And that shift of paradigm we owe to the Polish Cipher Bureau, because when the Cipher Bureau faced the challenge of Enigma in 1928, its commanding officer made a revolutionary decision to employ the mathematicians. I would not like to delve deep into the subject and to explain why he did so. Yes, he had some good reasons to try this solution, but he implemented a very, very long-term strategy. He first started with a cryptography course for a selected group of 26 mathematics students from the University of Poznan. And then the best from that group were recruited for a branch office of the Cipher Bureau, organized specially for the purpose in Poznan, so that they could complete their studies, working in parallel. And they've been doing their apprenticeship in the code breaking for 3 years, without ever having heard the name of Enigma. It was only in 1932 that 3 best of them were transferred to the headquarters of the Cipher Bureau in Warsaw, and then they faced the challenge of Enigma, and that investment in the code breaking course and in the apprenticeship paid very handsomely off, because Marian Rejewski was able to break the cipher that was deemed by the other code breaking agencies of the world as unbreakable within 3 months altogether. It took him 3 months to revolutionize the code breaking, because so far code breaking was all about linguistics, and suddenly from his success on, it was all about mathematics. And it led to the present situation where cryptography and the code breaking are nothing else than a branch of the applied mathematics. So it was absolute revolution. By the way, during his work, Marian Rejewski transformed his knowledge about ciphering machine Enigma into 3 mathematical equations. And those equations were very hard to solve, because those variables you see in the equations are not the integers or real numbers we are used to. They are the permutations, the term from the group theory. And there was simply no theory around which would permit to solve this kind of an equation. So Rejewski had to work out the missing theory himself, which he did. And later on, in the 1980s, one of the British codebreakers who participated in the wartime workings in Bletchley Park, Jack Good, described one of the theorems that Rejewski formulated in 1932 as a theorem that won World War II. Theorem about the product of permutations. But that was only one of the revolutions caused by the Polish codebreakers. The code breaking has double meaning. It can be analyzed as a scientific discipline, but I don't think that the Cipher Bureau was doing so. Cipher Bureau was interested in having the results now. The sooner the better. And therefore the time was also a very important factor in the work of the code breakers. So Marian Rejewski with his colleagues made a decision which was equivalent to a second revolution. They decided that the natural adversary for the ciphering machine is another machine assisting the cryptanalysis, assisting the code breaking process. And therefore, in 1935, they created a very simple electromechanical device which is called cyclometer, which was the first machine assisting the code breaking process. A bit later, during the Munich crisis in 1938, the Germans introduced some changes into Enigma construction and into Enigma operating procedures. And those changes required novel approach, required changing all the methods of breaking Enigma cipher used by the Polish team so far. And Marian Rejewski has demonstrated his genius in that period, because starting from September 1938, within a month, he invented the idea of a new device, which he called Bomba. God knows why. There are some disputes within the codebreakers and their families. What was the origin of the name? But let's stick to it, because we have no better. And company AVA, which was cooperating somehow with the Polish intelligence service, managed to manufacture within another month 6 copies of the device. Can you recognize the name, by the way? Bomba. Bomba. What was the name of the Turing's construction from World War II? Bomba. Bomba, as far as I remember. So Turing was a decent scientist, and when he was manufacturing the designs, when he was working on the designs of his famous device, he knew perfectly well that its construction represents just an extension and the development of its predecessor, of Rejewski's Bomba. Therefore, he used this design after its original. Well, Poles were lucky enough to escape from Poland in 1939. They were installed somehow in France. Unfortunately, the French did not assure the conditions which would permit the Polish team to participate creatively in the further code-breaking process during World War II. I would say that their genius been largely wasted. Fortunately, in July 1939, a couple of weeks before the outbreak of World War II, Polish codebreakers convened a meeting in a small locality called Pyry near Warsaw, where they transferred all their knowledge of all the theory behind code-breaking enigma, behind the machinery they are using, to their French and British colleagues. That meeting, it was a foundation for the cryptanalytic effort of the Allies during World War II. Without that meeting, neither the British nor the Americans would be able to break enigma so soon and so effectively during World War II. God knows what would happen to our continent. The scientists and historians agree on that the enigma code breaking has shortened World War II at least by 2 to 3 years. So if you take into account that the price for every year of that conflict was 10 million human beings, they have saved a number of millions of human beings. And I would say even more, because if the war in Europe lasted in the second half of 1945, the first nuclear bombs would probably explode not over Japan, but over some German cities in our continent. So the code breakers saved our continent from the nuclear war. Well, fact that over 200 Turing bombs were being used in Bletchley Park and in the outstations does not mean that traditional approaches in automated computing were given up. In the same Bletchley Park, there existed a section which was called Freebornery, after its leader, Freeborn, where a huge number of traditional card tabulators and sorters was used to compute so-called a tetra catalog. Tetra catalog was nothing else than hunting for the repeats in German messages 4 or more letters long. If you catch a repeat in an enciphered message, which is 4 letters long, you may be absolutely sure that it's not an accident. The two messages are somehow linked with each other. And Turing was able to exploit that fact in his specially designed method of attack on the Kriegsmarine ciphers, which was called Bombarismus. But the foundation of Bombarismus was functioning on that section of traditional sorters and tabulators. Then the scale of the challenge before the code breakers was still more extended, because in 1942 the first transmission of the new device, new ciphering device, were intercepted in the ether. The Germans introduced a special device, Schlüsselzusatz 40, which was used to encode Teletype transmission. Normal Enigma messages were sent using Morse code. And that device was encoding and ciphering Teletype transmission. It was a very fortunate situation, because while getting that device into full swing, they've made certain errors. In particular, they've sent one very long message, 4,000 characters, twice, with the same key, which permitted the British code breakers to not only break the cipher, but also to recreate the device that was used to generate the cipher. The recreation was called His Robinson. His Robinson was the first device used to break the Teletype ciphers, which were called altogether fish by the British codebreakers. And that device was working on a very simple principle. It compared two patterns registered on two Teletype pipes, which were rewound at a very high speed through the device. But there were no devices available in the market which could count the events happening in such a short intervals. And the search for proper counting equipment led the British codebreakers to a British physicist, Will Williams, who was famous for his research in the field of elementary particles. And to count the elementary particles, he constructed before the World War II a special counter. And that counter was used to count the events generated by the two Teletype pipes, to count coincidences between those two types. Note, please, that that's a Williams, by the way. Note that this device has a very interesting structure. From those lamps, we may judge that it is counting in binary form. It's 0 to 4. But the representation of the digital values in that device was perfectly analog, because 0 was coded by a carrier of certain frequency, and 1 was coded by the same carrier wave, but shifted in phase by 180 degrees. So the perfectly analog representation of strictly digital values. Beautiful example of the transitional nature of this solution. In 1942, German Kriegsmarine prepared a surprise for the Allied codebreakers. Normal Enigma, used by the land forces and air force, used 3 rotors. The Kriegsmarine, or precisely the U-boats only, introduced new version of Enigma with 4 rotors, as you can see. The normal British bomb could not solve this problem fast enough. Yes, it was possible probably to break also the cipher of the 4-rotor Enigma with a Turing bomb, but it would take months or 2 or 4 when the information gained from the decipherment would lose any operational value, and therefore it was necessary to construct a new bomb. The problem was entrusted in the States to an American engineer. His name was Joe Dash. Joe Dash worked for an American company, National Cash Register. And he had one disadvantage from the point of view of the American Navy who employed him. He was of German origin. Therefore, he was subject to severe limitations in his private life during the entire time of this project. One of the officers supervising his work was sleeping in a sleeping room opposite to his marital sleeping room, in his private home. So I understand that he was doing his best to complete this project as soon as possible. What is important? Important is fact that there is a natural physical limitations of the rotating speed of the rotor of this machine. And Dash had to reach that limit or even exceed it. Therefore, it was impossible for the machine to stop once the proper solution was found, because of the inertia of the rotors. Therefore, Dash designed that part of the machine. memory, electronic memory based on a very early and almost forgotten electronic valves. And it worked. When the machine reached the proper position, signifying the solution of the key, that circuit was remembering current position of the rotors, and then on controlled rewinding the rotors to the proper position. That's a very ugly, very unelegant design. Therefore, Dash had many problems with his own design. And those problems led to an incident which, for me, is very significant in this story. One day, when Dash was approaching the happy final of the project, a message came in from Washington. Interrupt the project, destroy all the technical drawings, destroy the prototypes, and restart your work, but this time working on a purely electronic construction. Okay. That message was just an example of the discussions taking place in the circle of the codebreakers. The codebreakers during World War II were facing continually changing challenge of the German ciphers. The Germans were quite good in code making. I know enigma messages which haven't been solved until today. And the Germans introduced from time to time some minor or bigger changes in the construction of their equipment or in the operational procedures, which were continually defeating all the methods of attack on their ciphers that Allies were able to invent beforehand. And therefore, both British and American codebreakers were continually thinking about invention of something they called a universal code-breaking machine. A machine that could be somehow configured to attack not specific, but almost any cipher by simple reconfiguration. And it was, of course, impossible when the operating principle of the machine, or the operating procedure of the cipher, were somehow encoded in the hardware. And therefore, a group of American codebreakers gathered in the cryptologic organization of the American Navy was dreaming about the construction of the universal code-breaking machine, and they were able even to dare the construction of the electronic device in 1943. This is Ralph Dash. This is Ralph Meader, and with him in the photograph you see Joe Dash's wife. That's the only preserved photograph of Ralph Meader. That's precisely the officer who was supervising Joe Dash's work living in his private house. So he was intimate with the project, one might say, to the extent that permitted him to say no to the stop order he received from Washington. He knew that the construction of that dream, the universal code-breaking machine, would take a year or two. And in the meantime, the Allies would lose the war in Atlantis. Because it was 1943. U-boats were sinking ship after ship in Atlantis. And the Allies were blind. They couldn't break enigma for nearly 1 year in that period. So Dash, Meader knew perfectly well that if he executes the order just received, that period will be even longer. On the other hand, he knew very well that the Dash's project is progressing pretty well. And he was right, because a month after that, the American bomb started to work properly, permitting to break the ciphers. Please remember this episode, because this episode represents kind of an epitome of a dream by the British and American codebreakers regarding the construction of the universal code-breaking machine. And of course, meeting their dream in the wartime was impossible. But we will see what will happen next, when the hostilities are over. That's, by the way, one of the few preserved pictures of the device, which was most probably one of the reasons for the stop order. It's auto-screecher. Auto-screecher was not designed as a code-breaking device from the start. It was conceived as an engineering prototype because it used a relay technology. It was not fast enough to surpass the bomb, no matter which one, British or American. But that was an engineering prototype for a device that was being constructed in parallel and was called super screecher, fully electronic device, which was designed by the American codebreakers as one of the variants of this universal code-breaking machine, because it was electronic, it could be programmed arbitrarily. Unfortunately for the Americans, the first prototype of super screecher was already in 1946, when it was completely obsolete. But then we come to the next challenge. You might know that one of the methods of attack on enigma ciphers invented by the Polish team still before the outbreak of World War II were so-called Zygalski sheets. This is an example of a fragment of the Zygalski sheets, and in my private archive I've got a letter, a post-war letter between Marian Rejewski and Henryk Zygalski, two key members of the team, the only ones to survive World War II. And Zygalski states in that letter, "Do you remember how we planned to transfer the content of the Zygalski sheets to Teletype tape and to search for repeats comparing the contents of both tapes?" And that is precisely the very idea that the British were able to implement, not during their attack on enigma ciphers, but during the attack on fish ciphers. This is a famous Colossus. The famous Colossus, well, some people describe it as the first digital computer in the history of the world. I wouldn't agree with that. I know anything depends on the definition. And we can shape the definitions to fit almost any thesis. But as far as I know, the only computation, general type computation that Colossus was able to execute was multiplying two large numbers. One of the young mathematicians working as the operators of Colossus managed to manipulate the contents of those two types being compared so that the counter computed the product of the number contained in both types. But probably more important than the device was the fact that its designer, Tommy Flowers, was able to convince his environment that electronic and vacuum tubes represent a viable technology. When he presented first designs, first plans for the construction of Colossus, there were many people who rejected the very idea of constructing of an electronic device for two reasons. First, the device containing some 2000 vacuum tubes will not work at all. And second, even if it works, medium time between failure will be counted in minutes. Fortunately, Tommy Flowers was using the vacuum tubes in the telephone circuits he's been designing before World War II. And he knew very well that if you assure proper, stable working conditions for the vacuum tubes, in particular, you don't switch them off and on, they work quite reliably. And he was able to design the device which worked perfectly well. 10 copies of Colossus were constructed before the end of World War II, and all of them behaved quite predictably. Doesn't mean that they were of a very computer type. Yes, they were digital. You can see a fragment of a blueprint for Colossus, or you can see a perfect example of the digital atom. But there were some idiosyncrasies, even in the construction of the computer, due to the wartime shortage of the vacuum tubes. And here you have, for instance, biquinary counter. Colossus was counting in a very particular way. It didn't use the classical ring counters. It didn't use BCD notation. Every decade counter consisted, in fact, of 2 counters. Of one counter counting to 2, and the second one counting to 5. And both represented a decade altogether. So, from the engineering point of view and from the theory point of view, Colossus was a very particular machine. Later on, the Americans brought to Bletchley Park their construction, which was called Dragon. No. Nothing to do with fire and fables. Dragon was called Dragon for a very simple fact that it served to drag the crypt along the cipher text. So, crypt, the probable text of the message, was somehow remembered in a relay memory, and then this device was checking whether that crypt could be represented in consecutive fragments of the cipher text. The device didn't serve long. The Americans forgot to check that the relays they are using are proper ones for fast switching. And they were not. So it ran a few hours. But soon thereafter, British constructors somehow adopted the idea and constructed their own construction, Aquarius, which is a very special one because it stored the crypt not in a relay-based memory, but the capacitor-based memory. And as you know, capacitors discharge, so that the information contained in this type of memory needed to be refreshed periodically. Yes, ladies and gentlemen, the first example of dynamic random access memory. It's very interesting that this idea was forgotten immediately after World War II. And the constructors of first computers were using delay lines or CRT memories. The prototype was ready. In the meantime, there was another thread in thinking about the automatic computation, which was very heavily followed in the States. Vannevar Bush, well-renowned scientist, but also a very powerful person in the American administration, was pushing through his idea of so-called MEMEX, which was based on the optical comparison of 2 pieces of information. And here you've got a clear indication of how it worked. If you compare 2 numbers superimposing both, and you put light through that, when the information is not the same in both pieces, the area covered by those numbers will be larger than in the case of any of those numbers separately. Only in an exceptional case, when there is a coincidence between both pieces of information, the quantity of light going through will be precisely the same. And Van Nevar Bush constructed a number of the devices based on that principle. Two of them were actively applied in the Allied code-breaking process during World War II, HIPO and 5252. Unfortunately, both proved to be slower than Colossus, and unfortunately, one of them was ready in June 1945, a bit too late. Now, we are facing the situation when war is over. The entire staff of Bletchley Park gets demobilized within about a month, and the place where still a couple of weeks ago some 10,000 people were toiling breaking German ciphers is empty. Two crucial people responsible for breaking of both Enigma and the fish ciphers decide to return to the universities they were working in before the outbreak of war. I mean, Alan Turing, who was responsible for the British part of Enigma code breaking, and Max Newman, who was responsible for the theory of attack on the fish ciphers. It's interesting because Max Newman had a very, very strong positions at Cambridge, but he didn't decide to return to Cambridge, and I will show you in a minute why. Max Newman decided to create a new organization at the University of Manchester, but he managed to do something more. He managed to save a couple of metric tons of parts from Colossus being dismantled, and to use those parts for the construction of the new computing device. Alan Turing joined the National Physics Laboratory, and using his wartime experience, already in 1946, he presented a memo outlining precisely and in a very modern way the construction principle of a device which, according to any definition, represents a modern electronic digital computer. Unfortunately, National Physics Laboratory was funded from the public money. And as far as I know, Britain was not particularly resourceful just after the end of World War II, so that money was flowing in rather leisurely. And he couldn't complete his project. So, Turing, disappointed a bit about the progress, decided to join Max Newman at Manchester. And that's precisely the reason why Max Newman has not decided after the end of hostilities to return to Cambridge. That is Meccano differential analyzer at Cambridge Computing Machinery Lab. Newman knew very well that there is at his native university a special organization, a special laboratory dedicated to the automated computation. But he knew also that the direction taken by that organization is a bit obsolete, because at the end of World War II, devices like that, differential analyzer, were already completely obsolete. So, those gentlemen, those wartime codebreakers met at Manchester where they were supervising team responsible for the construction of the first digital computer with a stored program ever. I will not tell you a word about that because you know this history better than myself. And in fact, on July 18th, 1948, that machine executed this piece of program, this piece of software. The digital age was born. But what I've told you so far describes the situation on one side of the big pond. Now let's skip to the other one. Americans launched a number of very interesting automated computation projects during the wartime, and probably best known of them was ENIAC. Well, what you see at the screen right now is nothing else than programming ENIAC. Ladies switching, and in a moment you see the guy who will be exchanging modules in the construction of that device, are writing software, or they're loading the software into the memory of that machine. And ENIAC was very powerful. I'm not measuring that in tons, metric tons, because yes, it was about 20 metric tons. 20,000 electronic valves. 12 accumulators, 4 multipliers, a lot of specialized circuits, but it was not flexible. It was not flexible, it couldn't be used for a different purpose, which we will learn in a moment. But, more or less at the same time, 3 American codebreakers who served for the American Navy and who were responsible for a construction of several specialized machines for the codebreaking organization of US Navy, William Norris, Howard Engstrom, and Ralph Meager, whom we already met, decided to continue with the occupation they enjoyed during the time of war. They wanted to continue to construct the electronic computing machinery for the American Navy. And so they've created a company which was called ERA, Engineering Research Associates. As another member of the staff of ERA, James Pendergrass, a young officer of the American Navy, his name was not present on a title page, but he was one of the people responsible for that document. That document does a summary of the state of art in the area of automatic and electronic computing. It's been prepared by ERA in 1946. And it's been declassified since then, and it's a very interesting lecture. I recommend it to all of you. But the theory was just a part of ERA's occupation. ERA was in a slightly privileged situation because it had many orders from the American Navy. Orders for specialized machinery, like for instance, first examples of the magnetic memory, predecessor of our hard drives. Does anybody remember hard drives now that we are using only solid-state devices? Engineering Research Associates was the first company dealing in the United States with electronic computing, and dealing successfully, because what you saw a moment before was the first device the company was able to deliver to the American Navy. It was called Atlas. Also, successful stored program computer delivered in 1950. But ERA and its managers decided that their construction might be of certain interest also for the private sector, not only for the Navy. But it was so universal that it could be used for various purposes. And therefore, they managed to convince the American Navy to give them permission to offer the same design also in a private market. And they called it ERA 1101. Why this number? Because the original computer Atlas was delivered to American Navy on so-called order number 13. The number is 13 binary. So we had one celebration, one reason for celebration. The execution of the first program by the stored program computer by the Manchester Navy in 1948. And ERA 1101 was the first electronic computer available and offered commercially in the world. Remember, please, that people behind both projects and both successes were the ex-wartime codebreakers. I'm speculating why they were so much interested in the electronic computations and why they were so successful in that field. I realized that engineers and scientists active in other projects took a slightly failed approach. They ill-defined their goals. They were thinking literally about automating of the computations, understanding those computations as arithmetic operations, as addition, multiplication, and so on. While the proper answer was not the arithmetics, was not the algebra, it was logic. And we know now that there is a number of generations of philosophers and of mathematicians who were trying somehow to formulate a universal theory of philosophy and mathematics, unifying the field of arithmetics or algebra with that of logics. But they had very limited influence on the computing machinery. It's surprising. It's surprising because that was the only way to go. I would like to share with you my thoughts about the reasons why the wartime codebreakers were so interested in the automatic computations and why they were so successful. And let's start with the nature of the problems various groups were facing. You might know that ENIAC was designed primarily for automating the calculations of the ballistic tables used by the artillery. Absolutely wartime purpose. And if you take a look at the ballistic equations, they are simple. They are getting more complex when you take into account other factors, like the rotation of Earth, like the atmospheric pressure, like the wind. However, there is one fundamental thing that remains valid. All of those equations are of continuous nature. They are not discrete. They are analog. They are continuous. And the same story we observe with another source and another area of wartime progress in science and research, nuclear research. Ladies and gentlemen, I've taken those equations from the textbook entitled Do-It-Yourself Atomic Bomb or something like that. So don't ask me what do they represent. I hardly understand them myself. All I know that they represent some hydrodynamical problem. You might ask what the hydrodynamics has in common with a nuclear bomb. Okay, I've learned from the textbook that in the environment of the nuclear explosion, the solid components of the nuclear bomb start to behave like liquids. And therefore, computing the parameters of the front of the shock wave, the position, shape, and velocity of the shock wave is crucial for the construction of the atomic bomb, because it determines whether the chain reaction will happen or not. And again, those equations are far more complex, or at least seem, for those of us who are not very well versed in mathematics. But again, they are continuous. They are classical differential equations of strictly continuous nature. They have nothing to do with digital world. And this is a typical challenge of the codebreaker. It consists of separate, discrete units of information. Depending on whether you are dealing with a code or a cipher, you are dealing with words or letters, and each of them needs to be treated separately. So one might say that the nature of the codebreaker's job is discrete, is digital by its very nature. But that's not all. It's a fundamental difference in a quantity of work necessary to solve the problems. This is a group of women employed in a group called T5, T from theory, in Los Alamos. When the physicists working at Los Alamos over the nuclear problems realized that they have to solve some really complex differential equations and they simply have no time for that, they've realized also that some of them came to Los Alamos with their wives, who are dying of boredom looking at the surrounding desert. And if one could decompose the solution process of differential equations, we might employ our wives. That's precisely what they did. That group of young women contributed fundamentally to the construction of the nuclear bomb, solving the necessary mathematical problems. Another area where huge number of computations are necessary is administration and business. Okay, I have no better argument, but I come from the country, and I was born in a period where you could throw in an arbitrary number of people into bureaucracy. There was always a solution of throwing more people. So I don't know the business problem which couldn't be solved by throwing more people into it. There is a huge contrast in the work of the codebreakers. That's a fragment of a paper by Polish codebreakers describing the complexity of enigma. That number, ladies and gentlemen, is a number of possible connections within just one enigma rotor. One enigma rotor. And in translation, this paper says, the last figure can be summarized as follows. If every person living on Earth had tried one possible connection every second, the entire world would have been completed after 6 billion years. So, I guess that the nature of problems the codebreakers are facing is far more computation intensive than any other problem other specialities and other scientific disciplines could encounter in their life. The advent of the machine ciphers represented a complete game changer in the history of cryptology, and the Polish mathematicians attacking the enigma ciphers realized pretty soon that due to the sheer number of possible solutions, a natural adversary for the ciphering machine is another machine. It was a very fortunate event. The Polish codebreakers decided to share their experience with their British and French allies, and Grajek's ideas got almost directly into the hands of Alan Turing, because Turing's concept of the abstract universal machine presented in this seminal paper on computable numbers was focused around a simple but extremely powerful idea: how to decompose and represent virtually any problem as a potentially infinite sequence of elementary logical operations. It is historical and indisputable fact. Excuse me for a moment. Okay, I will try to do without technology. It is undisputable fact that on both sides of the Atlantic, the first digital and electronic computers really deserving that name, excluding the constructions like ENIAC, were designed and constructed by ex-wartime codebreakers. It's an interesting question for me, and I hope also for you, why this happened so. Why the codebreakers had some advantage over other disciplines, over representatives of other disciplines in the design of early computing machinery. And I think that there were several factors. The first one is the fact that cryptologic problems are discrete, are not continuous of their very nature. So the codebreakers had a tendency of looking at them piece by piece and not as a continuous equation. The second factor is the fact that the codebreakers tended to prefer logic to arithmetics. That the designers of other kinds of machinery were addressing purely computational problems, computational understood as arithmetic or algebraic. And the codebreakers were addressing purely logical problems. But there is also one more factor. All the other problems were based somehow in the existing laws of nature. They were addressing challenges resulting from the natural sciences. And as far as we humans know, the laws of nature are immutable. They do not change in our lifetime. While the codebreakers were facing the challenges that were changing quite frequently. Because the adversary, well, it's normal standard practice of the code makers to change the key daily, or to change the ciphering procedure at least 1 year. And therefore, the codebreakers were facing the reality when they had to face a new challenge every couple of months. And therefore, they were fed up that high with the idea of constructing the specialized code-breaking devices that were obsolete in about a year. And they were dreaming about the construction of the universal code-breaking machine. They had no chance to construct that universal code-breaking machine still in wartime. But once they were able to return to their academic work, it was precisely the ex-wartime codebreakers who managed to construct the first digital computers in the history of mankind. Thank you very much.
A couple of quick questions, and then I'm afraid, as I explained, Marek needs to go. Who'd like to ask a question? Yes.
Just a very quick thing. You were comparing the sort of analog world with the logic world, but something between that which seems to me to come somewhere into that is the business that came in abstract algebra, groups and rings and fields, which in my experience I got mixed up with pseudorandom sequence generation and so on. That seems to be a world between the two. Do you agree with that at all?
Not exactly, because the first attack by Marian Rejewski on enigma cipher was based precisely on a group theory.
Yeah, okay. But it had to be there, didn't it? Thank you.
Anyone? No. Marek, I do hope we have an opportunity to invite you back on another occasion when we can have more time to explore some of these fascinating ideas. And we wish you well, and we trust that your plane will indeed take you safely home to Warsaw tonight.
Oh, Roger, you know me, you know that I will make home even without the plane.
You have my mobile phone number. As I said, let's give it a as I said,